we've started looking at systems that undergo a bifurcation, a steady bifurcation, to patterns. So we're actually looking at large systems, spatially extended systems, and the characteristic diagram we had was that there's a control parameter mu, or bifurcation parameter, and depending on that parameter, the homogeneous state, which is like a base state, becomes unstable to different kind of modes. The modes differ in their wave number. And the typical diagram is that as you increase mu, there is some value mu c at which that homogeneous state becomes unstable to some wave number called QC here. And as you increase the parameter further, a whole range of wave numbers arises that destabilizes that homogeneous state. So it goes from like a minimal wave number to a maximal wave number. And we saw in the simulations that if you start with random initial conditions, that as expected, all the wave numbers outside that band decay. Well, we didn't measure that explicitly. We just saw that all the high wave numbers actually disappeared and only lower wave numbers remained. And then we also saw that as time progresses on a much slower scale, the pattern actually became more ordered. I mean, initially it was disordered. It was periodic in some, well, it wasn't periodic, but it was modulated. But as time progressed, the pattern became more and more regular and became periodic. And so we'd like to be able to describe that situation where we have a simpler equation than the original equation that captures the possibility of patterns that are not just, okay, that first, not only exactly at that wave number QC, but also at a wave number that's nearby. And then we hope that that would allow us not only to describe periodic patterns with a wave number that's like QC plus a little bit, let me call it epsilon Q, but also patterns that maybe have different wave numbers at different locations. They could look like that. So that's the hope. And that we would then be able to describe what happens when you start with initial conditions of this type, whether they relax or don't relax, and so on. So how could we do that? Well, imagine again an equation like we had before, like this Kuramoto-Sierczewski-like equation, or we'll use the Swift-Hohenberg equation, which is yet simpler, where we have some quantity psi, which in homogeneous, in the base state is 0 for simplicity. And we expand it in our usual form. There is a wave number e to the I qcx, and then there's an amplitude. And we allow now this amplitude to depend on slow time as always. And well, let's see what we could do. Let's continue. So what we actually want to have is that it actually is not QC itself, but slightly different. So we need to modify our expansion. So it's actually QC plus this small quantity, which I called epsilon Q. I mean, I don't know what epsilon is at this point. I just want to mark that this is probably a small quantity. And that's what I have. There should also be some small parameter in front. But since I don't know yet how to do this epsilon, let me not put an epsilon here. Well, this is just sketching, just so we see, oh, how should this work? And then once we understand how it works, then we could put the proper epsilons in and stuff. So the idea is, of course, the higher order terms in complex conjugate and all that kind of stuff. But the idea is that we could incorporate this object into this low amplitude, just like we did with the time, right? Before we had, in the half bifurcation in particular, we had like a fast time. And then we wanted to have also slightly different frequencies and modulations. And so we allowed the amplitude to depend on a slow time, a separate time. And we're going to do the same thing. We'll introduce a different spatial scale. We'll introduce two spatial scales. And so the amplitude will depend, of course, on the slow time as before, but also on a slow time. And it will look like that. And this thing here then would capture this modulation if simply, with a periodic function up here. So you could have looked at it the other way around. You could have said, well, we want to have a solution like that. Well, so I can write this as e to the I QCx times an e to the I epsilon qx here. And then I incorporate this into the amplitude and allow that to vary slowly. Okay, one way or the other, we introduce multiple scales in space in addition. So we have now, instead of having psi of x, we have psi of x and slow x. I guess you might prefer to first call this x here, this fast x, something else, to make sure that we have, this is the original x, and then there's a fast spatial variable and a slow spatial variable. And then the derivatives become, our derivative with respect to x becomes then a derivative with respect to this psi plus a derivative with respect to the slow x times the slow x by dx. And the question is now, how is the relationship between capital X and little x, right? So how can we get an idea how we should scale that? Before I do that, let me just sort of, for simplicity, say, well, let me not write xc here. Let me just write that also as x for simplicity. So my fast x in the following will be written just like the original x. Okay, so what can we say? Well, we're interested in systems that have these spatial patterns, which are stationary when they pop up, right? So that's the idea. And that's a characteristic feature of these systems, that they're reflection symmetric in space. You can ask why. Well, if they were not reflection symmetric in space, then you can argue that there's no reason that these patterns actually are stationary, as in that they just sit still. If one direction is preferred over another, you would expect that they actually move. And that's an interesting question. That's an interesting category of systems. We're not interested, I don't want to do that right now. So we're looking at reflection symmetric systems. So assume reflection symmetry. And then what does that mean? Well, of course, little x goes to minus little x. That's what we essentially define. But that also means that the slow x will also be flipped when we go reflect from one side to the other. And the original system is equivariant under that reflection, right? That's what I just assumed. That means the amplitude equation that we get eventually has to also be equivariant under those reflections. Now, we know that terms that show up in that equation eventually, they have to be something like dA by dt, and there has to be a absolute value squared cubed, because whatever we do, when there's no slow spatial variation, we have to get back the equation we had before. So in the absence of spatial derivatives, we have to have terms like this. And so therefore, these terms are invariant under reflection. And so what we can only allow, or what we expect either way, the terms that show up will also have to be invariant under reflections, and that means they have to be a second derivative. You can't have a first derivative there. Well, that's actually not exactly true. Let me not get into this. We can think about that later. I just say, the argument sounds right, but there's a subtlety involved which requires something, but let me not get to that. So it is true that if we do this expansion, as we say, right here, around that minimum, then you only can have second derivatives. Well, that means that the second derivative has to be the second derivative. Shucks, what happened here? Tablet is not cooperating. The second derivative has to be of the same order as a squared, right? Because we have to balance these two terms. There will be coefficients, of course. And that means that d by dx must be epsilon, order epsilon. And so that means the capital X is epsilon times little x. Okay, so that's what we expect. And well, then we can actually continue expecting, because I said, what terms should we have? Well, we expect the good old equation. I forgot about a mu term, so there should be a linear growth term, so that's dA by dt equals some mu times a. And then we expect a term here with a second derivative and some coefficient. And then there will be another term, a cubic term with a coefficient. And to leading order, it's not clear what else there should be. This is all that should be. So that's the equation we expect. Good. That is actually a very general equation, and I'll make comments about it later. But let's first see how we actually really get it. Okay. So let's consider a simple equation. Let's consider the Swift-Hohenberg model, which is a yet simpler model than the Kuramoto-Sierpinski equation. It was put forward by Swift and Hohenberg as a simple reduction of the convection equations, and it's not a rigorous reduction, but it is a good model that captures a lot of important aspects. So it is also for some scalar quantity, the psi, and it has the same linear term as the Kuramoto-Sierpinski equation that we wrote down. Well, the modified Kuramoto-Sierpinski equation, but it has a simple nonlinearity. It's cubic, which means there's no quadratic terms generated, which makes it simpler, and there are no derivatives in it. So it turns out, for instance, that it's variational, as in you can derive it actually from a potential, so there can't be any persistent dynamics, and there's a bunch of stuff one can say about it. Let's not worry about that right now. We'll just do our expansions, right? So what do we need? Well, the thing we need that we haven't done before is that here we have now a second, and actually because of the square, also fourth derivative, and we have to worry about what that means in terms of a slow variation. So let's calculate those derivatives. There's a little bit of algebra. So let's see. So we have that d by dx becomes actually d by dx plus epsilon d slow x. And so therefore, if we take the second derivative, we have to square this. And so we have the second derivative. And then we have the mixed product twice, which is the second derivative with respect to fast and slow. And because our final equation we expect to have a second derivative in x, meaning that the whole thing is order epsilon cubed, we have to go here also to order epsilon squared. So we have plus epsilon squared slow derivative. That's the second derivative. Now for the fourth. Okay, so we square this guy again. So we square this. Okay, let's do it. The fourth derivative becomes the fourth derivative with respect to fast, plus, and now we have to have the mixed product here. This mixed product gives us 4. I mean, gives us yeah, so I like, you could square this, but I prefer thinking of this to the fourth power and think of my binomial coefficients. Either way works, but that's what I'm going to do. So I have to take the fourth term here, then I have a cube here and one factor here, and I have 4 of those. So I have plus 4, 3 fast derivatives and 1 slow derivative, and then has an epsilon. And then I have 6 where I take 2 of these and 2 of these. So I have 6 epsilon squared, and I take 2 fast and 2 slow derivatives. And there's in principle order epsilon cubed, but we don't need those because we only go to order epsilon cubed. Okay, good. So now we're equipped. Now we can write down our expansion and see what happens. Let me put this expansion still here. So psi is equal to epsilon times a of x and t, e to the I qcx. Qc turns out to be, in this case, 1. So this is e to the ix plus And then we need, since this is only a cubic term, there will be no quadratic term generated. So we don't need an e to the 2ix. So we actually have just an epsilon cubed d e to the 3ix plus higher order terms plus cc. Of course, the d is also slowly varying, but turns out we don't need it, so I didn't pay attention to that. Okay. What do you need to do? Well, we just plug in. Order epsilon, let's see. Order epsilon, that's the leading order terms. What I did not do yet is we also have to say something about the control parameter r, right? So here's our r, and we want to be close to the minimum. That's the idea, right? Let me emphasize again why that is important. As you know, if you increase r, well, here I wrote mu, but it's the same thing. So if you increase r, if you go all the way to here, if we were expanding around here, then we would have already a finite width of these wave numbers. And so that would not be small anymore, right? What we need to look at the limit where this range of wave numbers goes to 0. And that range of wave numbers goes to 0, of course, at the minimum. So we need to do an expansion around the minimum. So r has to be close to the onset. And in this model, the onset happens to be at 0. So therefore, r is actually, let me write it here. R is epsilon squared mu2. Okay, good. So now we can expand. So at order epsilon, what do we get at order epsilon? On the left-hand side, we get nothing because we get 0 because the time, there's only slow time, which is order epsilon squared again, and then psi is order epsilon. So this is actually an order epsilon cube term. Same thing here. This is an order epsilon cube term. This thing, okay, so this is where the fact that we picked here the critical wave number, meaning QC equals 1, because then this derivative here is -1 cancels on this linear part disappears too. So we actually, if you want to write it formally, we have the equation L0 of psi 1, if I call this the order epsilon term, as in this guy, is equal to 0, and L0 is equal to this operator d by dx squared plus 1 squared. And we see that L0 of e to the ix is equal to 0, and L0 is singular. We're not surprised because that's all these expansions, right? So, but just to remind ourselves that even in this context, it's the same business. So that we've solved, doing the linear stability analysis, we've solved the order epsilon term. Then the order epsilon squared, as I said, there's nothing coming from here, but I was a little bit cavalier, as in not saying anything about these terms, because at order epsilon squared, we get something from there. We get, this is epsilon together with a psi, this makes epsilon squared, as does this. So we need to write those down. So what do we get? At order epsilon squared, we get, we have to take fourth derivative, 1/4 derivative. Okay, what is that? 1/4 derivative. So if 0 is equal from the fourth derivative, we get this term, which is 4 times 3 fast, 1 slow derivative. That's 4 times 3 fast. 3 fast makes a minus I, and then 1 slow derivative, dA by dx, times e to the ix. Okay, let me not write that down. Plus, and now we need to go back. We also have the mixed term here, which is 2 times the second derivative. So we get 2 times the second derivative plus 2 times the second derivative, which has this term to contribute, which is again a factor of 2, and that has actually 1 fast, 1 slow. So 1 fast makes I, and 1 slow makes dA by dx. And you see that's actually 0. So that cancels out. You can you can think about it and show very easily that that term drops out exactly because we're at the minimum. If we were not at the minimum, and formally you could do that, you can do the same expansion here, then the quadratic order, it would not drop out. Then you would get a first derivative, but that would have a term I in front of it, right? It has actually an I term. And so that looks as if it was going to contradict our statement about the fact that the coefficients have to be real. And as I said, that argument is correct, but not quite correct, so to speak. And the point is, under reflections, you also have that, of course, A goes to A star. And when A goes to A star, that means you have to talk about what happens to the coefficients. You have to take the whole equation, the complex conjugate. And therefore, when you do that, that coefficient I here will also flip sign. So the point, all odd derivatives have to have imaginary coefficients, and all even derivatives have to have real coefficients. Okay. Just to be more precise. In any case, in our case, expanding about the minimum, which is the most commonly thing to do, because that's sort of where the most power is, we don't get anything at quadratic order and at order epsilon cubed. Finally, we get something. We get on the left-hand side, we get dA by dt slow. And then we get, let's just look at it. We get, of course, from R, we get a mu2 times A. Then we get something from the derivatives, which we have to look at. And we get the cubic term, which is as before. We had that before. This is going to be 3. Oh, no, we haven't had it. But let me just tell you, it's 3 epsilon minus squared A. You can calculate that very easily. So that's first, let's write down these terms. So we have mu2 times A. And then we have a minus 3 A absolute value squared A from the cubic term. And now we have to just get the terms from the derivatives. At order epsilon squared for this guy, we get something from the fourth derivative, which is 6. 6, too fast, too slow. The too fast make a minus sign, so we have minus 6, two slow derivatives. Minus 6, 2 slow derivatives. And then we have, again, this is a mixed product. So we have 2 times the second derivative. We need the epsilon squared terms. We have 2 times the second slow derivative. So we have plus 2 second slow derivative. Okay, done. Let's just write down what we have. So we see a nice equation. So we actually have dA by dt is equal to, and let me write it like that, is equal to 4 times the second derivative with respect to space, plus the control parameter minus the saturation term. So that's the equation we derive explicitly. And it has, of course, the promised form. Of course, because I've done it before, so I knew that. Okay, so there's mu, there's delta, there's gamma. We have mu is our mu2, delta is 4, gamma is minus 3. Okay. So this equation is actually a very widespread equation. It's called the Ginzburg-Landau equation. Ginzburg-Landau, because it goes back to an equation by Landau, Lev Landau, who in the theory of phase transitions derived equation for what's called the order parameter, which in phase transitions, in second order phase transitions, is sort of like if you have a liquid gas transition at the critical point, the order parameter would be the density. It's the density that changes in a phase transition. Or if you have a ferromagnetic system where you have magnetization, that ferromagnetic transition is characterized by the magnetization of the material, of the iron, say. And that near that second order phase transition, he showed that that order parameter satisfies an equation like this. Well, this is more for historic content because this is more complicated. Obviously, the temperature, the magnetization and the density, they're real quantities. So the Landau equation is actually an equation for a real quantity. And the Ginzburg-Landau equation of Vitaly Ginzburg added the spatial derivative term to allow for space-dependent magnetization, so you could have fronts propagating and stuff like that, where the magnetization invades the system and stuff. Anyway, so that's the original Ginzburg-Landau equation is a real equation for a real order parameter and has real coefficients. So here we also have real coefficients because of the reflection symmetry, but we have a complex amplitude. So one calls this the real Ginzburg-Landau equation, referring to the coefficients actually, because we'll see later that there's also a Ginzburg-Landau equation with complex coefficients. And so you need to discriminate those between those two because they have very different properties or quite different properties. So that's the real Ginzburg-Landau equation. And you see it is actually very similar in some ways. Well, for a moment, forget about the spatial derivative. We still have this special nonlinearity, which always allows the phase shifts. And so if you now think back when we had the Hopf bifurcation, there that phase shift symmetry allowed us to look at solutions that have a slightly different frequency. And so we had like solutions e to the I capital omega capital T. And now similarly here, that nonlinearity allows us simple solutions that are periodic in A. So a simple exact solution is given by A equals some magnitude R, or maybe I shouldn't call it R because it was our control parameter. Let's call it curly A times e to the I capital Q x. That's obviously a solution. Well, obviously, because when I plug it in, I see that I get minus 4q squared plus mu2 minus 3a absolute value squared. A could still be complex if I feel like it. And so I see that A magnitude is given by square root of mu2 minus 4q squared divided by 3. Fine. Well, let's look at that. This solution depends on the wave number. Its magnitude depends on the wave number. And so you can convince yourself that it's not hard, that you see when Q is equal, when Q squared, when this numerator here is 0, that's exactly the neutral curve. So that means what we have found is that we have found now periodic solutions that span this whole width here in the neutral curve, and the amplitude goes to 0 at the neutral curve. That's not completely surprising because if we hadn't done any slow spatial variations, we just had taken the periodic box, we would have seen the following. We have seen the following. If you take a wave number here, then there is a supercritical pitchfork bifurcation at the neutral curve. And that means at the neutral curve, the amplitude has to go to 0. So therefore, we're not surprised that if we expand here and then change the wave number, that wave amplitude also goes to 0. So that makes all sense. And so we have now a continuum of solutions with different wave numbers, and they're all steady. But in addition, we don't need to have A be periodic, right? We now have a full PDE for A. We can start with arbitrary initial conditions and ask what's going to happen with these initial conditions. And so in principle, this must be able to now capture solutions as we envision them, that they have wave numbers that vary in space. They can't vary a lot because we say we have captured everything in a slow spatial variation. So the Qs have to stay within a narrow band, but they're not all the same. So you can have a slightly higher wave number here, slightly lower wave number here, and so on. And this equation will tell us how this behaves, whether it relaxes or not. And that's something we will have to investigate next. That's actually the next topic, to see what can we say about solutions of this equation, and can we describe that relaxation in a yet simpler form. But I think that's enough for now. We've derived a nice real Ginzburg-Landau equation, which in itself has many interesting properties, and we'll just touch upon some of them.